So this time I'm actually gonna, one thing I'll say before, that's not relevant to the courses, but it's relevant to the video, is that I'm not gonna edit this one. Like, I'm just gonna put timestamps as to where things are, because if I edit it, that means people won't get it until this evening, because my work computer doesn't have video editing software I can use. So like, yeah, basically, I assume
Editing takes
people would
forever.
would rather a like slightly less polished product that comes out many hours earlier.
Yeah.
Since this is pretty close to homework due dates. Yeah, so the first thing I'm going over is problem 6, right? Yeah, problems from homework 6.
8.
Yeah, whatever it's called. The only question on homework 6. So what did you get for the middle part? We can start with that. Right.
Well, okay, so you can, so I threw out the, so I threw out the middle, I labeled them PQR, and I threw out the middle state Q as an intermediate state.
Okay, so
And
I'm just gonna do one thing at a time. P, really big states. Q, R, right? Okay.
Yeah. And then, so basically, if you throw out Q, then you
Okay.
can either go from P to R directly not using Q, which you can't, but like in theory, like this is the formula, right? It's R P P O. So the regular expression R sub PR, and then over the states P, Q, and R.
So sorry, do you want to write it, actually?
It's like,
I'm interested in what you mean.
this is what you gave us in class. So you have a regular expression to
Okay.
go from the start state to the final state.
Okay. Right.
Over all 3 states
Okay.
is equal to
Never seen that notation. That's interesting.
a regular expression where you just go from P to R using
Yes.
only these 2 states because you threw out Q.
Okay.
Plus, so this is a union.
Plus whatever gets you to Q.
Right. So then this is R P Q over P and R, and this is R Q Q. So then you get to Q, you can loop as many times as you want.
Yep.
And this is the
It's
starred
interesting.
one. This is starred. That's a very bad star. And then R Q R of
Whoa, that is a lot of text.
Yeah, it's
He likes
this is
very formal notation for everything. I think a little more abstractly about it, but maybe this is more concrete and nicer. For
well,
students.
it's very like algorithmic.
Yes, it's very algorithmic, which is, I would say bad for my intuition, but really good for getting it done, right? Because there's like a very sequential, like step-by-step process you can take for doing it.
I didn't think it was.
Or maybe not.
I didn't think it was too unintuitive.
Okay.
Because basically,
Yeah.
this is saying like, can I go from there to there
Yes.
and not go through this, which you can't in this one.
Oh, I see. So, yeah. So what you're doing is just like his full algorithmic approach to this, even though some of the parts of this algorithm are just going to be empty, right? Like,
Right, for this case, but
Yeah,
like,
for this case.
this is, I guess, is a general thing
Mhm.
that works. The only thing,
Yes.
I think this would get really bad if you had like 4 states and then you threw out one and then you would have to like recurse and go
Yeah.
down to these.
So I think my guess is this will always work. It's definitely slower than like, there's certain machines I can imagine that would have very simple regular expressions.
And it would take you forever.
But
to
it would
do
take
this
you a
way.
while to do it this way.
Yeah.
In which case you would want to just like look at a bunch of states and see the intuition as to like, oh, I see what these are kind of doing at this high level. But that's kind of like a zero-sum game, right? Either you see it or you don't. This always works.
Right.
So this is empty, right?
Yeah, that's the empty set.
And then for P to Q, what is this? Sorry. How
So
do you read
you
this
go
notation?
so it's
Going through P.
you can go from P to Q, and you can use P or R as an intermediate state, but you cannot use Q as an intermediate state. Not that that matters here, but
Okay, so really it's just P to Q, which is A, B.
A or B, yeah.
A or B, right?
Yeah.
Okay, so A or
A plus, I
A
think
plus
they use
B.
for regular expressions.
I have seen people
But no, or would be.
overload. What?
Or would be fine. I don't know, whatever. you
What
want.
does he use in class? If he
He
uses
uses
plus,
plus.
yeah,
He
yeah,
uses
I'll
plus.
use plus. That's fine. Right? Yes, he does do that. So
So we're taking
A
or
plus
B.
B And then
So now you're at Q, and you can go leave Q and then come back as many times as you want, using only the states P and R to do that. So this is like the bulk of the problem.
Yes. So going from
So there are
Q to itself using the other states, which this is what?
B.
B, right? Yeah. And then this is A or B.
So yeah, at first I only saw the one path, which was to go to P and then loop back. And then I realized, oh, there's the other loop, which is to go to R and then to B and then back to Q.
Right. So we want an OR over those options, right? Because they're two kind of distinct choices.
Yeah.
Which is what? So the first one is A concatenated with
A or B.
A or B, right?
And then
this is all
plus
with
B.
With B
Concat.
union A B union like squared, right?
Yeah, you could do that.
'Cause you
I wrote it twice, but yeah, that's fine.
Well, we defined this last time actually, right?
Right.
We just accepted that this for finite values is fine.
Yeah.
Because we did like induction over concatenation.
And then you're gonna star that whole expression.
And then you star this expression.
And then the last part is just to get from Q to R, which is just B, so that's very straightforward.
Right. Okay. And so this is the regex?
Yeah.
Is what you claim? Okay, I believe that. This is almost certainly not the simplest regex to do it.
Yeah, I actually I did a couple of the simplification steps and then I was like, whatever.
Cool. Oh, he has like defined simplification steps, or
He gives the ones from Cozen, and so there are like 7 or 8 or 9, I don't know.
Wow, yeah, like this is gonna work, but man, that's a whole lot.
You don't have, but he says, yeah, you don't have to do them. He's like, Cozen loves to play with the algebra of regular expressions, and
I can tell. I'm not sure I love to play with the algebra. Like, I find it intellectually interesting.
When you get here, you're done. But I guess the problem is that when you look at this, it's not intuitive what's happening.
Yes. Because like, the way I would deal with the AB is you just like put an A or B at the end and then star the whole thing. Right? Like that's the way you deal with it. Mm-hmm. Because like if you are at R, you see all the ways you can get to R, and then you stop from P, of course, from the start state. And then you're like, okay, well then concatenate A or B and then star it. That's the way I like to think about it, because it's like, well, okay, how do I get to a start state? How do I get to a final state from the start state?
The only thing is you could go just one time and not concatenate A or B, or you can concatenate A or B and then go as many times, like each time.
So, a good point. What you need to do then is you need to actually like, let's see. So if you have a regular expression, let's say R, that gets you to, let's say you have a expression that gets you here.
Yeah, from P to R, without.
Yeah. What you actually need is to say, concatenate this.
I would say R.
With the way I want.
I would union it with A, B, R.
A
or B, R.
Or B, R.
Okay, yeah. No, that's perfect. Because then you can take 0 of those if you just want to do it once.
Yeah, you're right though. Definitely this needs to be inside.
Right.
So it's not quite as pretty as I wanted it to be.
But it is still very simple.
I like the intuition this gives of like, you're here already, just make sure you don't leave, right?
Yeah.
So that's the way.
It's just very specific to this machine where you have a loop from the final state to the start state.
Yeah. I think with most machines that are put in problems because they would just take too long if they were way too big, there is some way to abuse the structure of the machine that allows a reasonably simple regex. I've never seen a DFA I couldn't come up with like a reasonably simple regex for.
Yeah, if he gave one of these with 4 states on an exam and I attempted that method, I would run out of time. If I looked for some like logic or intuition, I could maybe get it.
That's basically. But like we were talking about, it's a zero-sum game. If if you can't find the intuition,
Yeah.
you're just like, okay, well, I'm screwed.
Right.
Whereas if you do this, it's probably easier to get partial credit because we see that you like are doing a process and like know how to do this, but like you mess up a step or something.
Mm.
But also, once again, yeah, it could take a really long time. So
It's good for computers, though.
I suspect that since he taught you this, everything he gives you
Will
even on
work
exam,
that way, yeah.
Yeah, will be simple enough to do this way. So I wouldn't worry about it,
Yeah.
audience. Okay, I'm gonna erase this. You cool with that? Cool.
Yeah.
Trying to get bold markers. I'm steadily trying to improve this video making process. Unfortunately, this is kind of like the pilot right now, so everything's a bit of a mess.
Yeah, so these computational homeworks, I think, are the they're the easier ones, and
Yeah.
then it's way easier to miss cases in your proof.
Yes.
Like this week.
Okay, so moving on. Let's see. What do we got this week? And then I'll put like a timestamp in the description for people to about this time. So we're talking about homework 7. So there's one question, right?
Well, there are a bunch of like due problems, but there's one.
What are we doing?
One graded. No, there's one
that-
graded.
There's
question.
one. Let's talk about the graded
Yeah.
one first, right? I think
Right.
that's what most
Let's
people
go right
care
there.
the most about. So let's see. I was still reading this a little while ago, so let's see. It doesn't say that. Okay. If H is a homomorphism and HA is regular, then A must be regular because it's possible that its inverse doesn't equal itself.
Mm-hmm.
That is true.
So
7.3 was.
So it's disproof by counterexample, basically.
Or 7.3. Regular expressions are closed under inverse.
Uh-huh.
Inverse homomorphism. But that doesn't get you this. Show there exists a homomorphism H in the set A such that. Okay. So. Let's see. A subset of this is regular. Right.
Mm-hmm.
Okay. So. So what's the process that's happening here?
So on the inside, first you're taking a homomorphism of some regular language.
Yep.
And you're going to end up in gamma star.
Mm-hmm. Do we know that's regular?
No.
I don't think we do.
No, because that's what we're trying to show, that it doesn't need to be regular.
That is not necessarily what
Right.
we're trying to show. We're trying to show that, I'm not saying whether that's true or not. What I'm saying is that, note that we need to show there exists a homomorphism H on a set A such that the inverse of H of A isn't back to A. But that doesn't mean that this isn't regular. Right?
Okay.
So it is plausible, that case makes it plausible that it's not regular. Well, let's just think about that even for a second. Do you see what I'm saying?
Yeah.
Okay.
Well, I was trying to think of it with an example because the alphabet soup is like harder for me to reason around.
That's fair. Yeah, that's a good idea. So do you have any regular languages in mind that you want to play with and
Yeah, like a very small
homomorphism on it? Here.
So like, let's say we have sigma is gonna be A and B, and then we need a gamma. Can't put a gamma. And it's gonna put alpha in this. I don't know how to draw beta, so we're
Don't worry about it.
gonna leave it out. And then the homomorphism, which goes between them, I was going to define as something like A maps to alpha, and then B maps to epsilon. So I'm just going to throw the b's away. And then I guess epsilon always has to map to epsilon. Does this meet the definition for homomorphism?
That's a good question. I haven't thought much about the definitions for homomorphisms, honestly, in my life, but let me give it a moment. That's why I just want to be careful, because I know that homomorphisms are not something I've worked with on a regular basis. Homomorphisms such that. So H is the homomorphism. And saying that H, X, Y. Sure. As long as strings are defined in a similar way, right? It's like, because H needs to be able to take in a string.
Right. So you could have like HAB here, and it would map to alpha.
Yep. I just wanted to make.
Which would also
you need to be careful to define.
Which
that,
would
right?
be H of A
So,
concatenated with H of.
So it's a function that takes a string, and for each character, it keeps the character in the same position in the string, right? And trades out A's for alphas.
Yeah.
Notice you could like. Okay, I guess the alpha.
So it throws away the B's and it trades the A's for alpha.
Mm-hmm.
So you basically get. So you want to show that, like an H of AB is going to be H of A.
Yeah, this is a great example.
H of B.
Mm-hmm.
And that's going to be.
Yep, you've got it.
Yeah, alpha, and then this is epsilon, and you're just gonna say, okay, like.
Yes. Okay. So. And then for what about the other side?
Okay, so now.
No, I was saying like. For this equivalence, you need to show that both sides are going to be equal. Notice though.
Well, I mean, I don't know that I did show that.
You didn't. Yeah, you haven't shown that both sides. So I mean.
I feel like they are, but.
They definitely are. You just want to be careful. So
H of A.
I guess to really do this formally, is this a proof? Do you need a proof?
That it is a homomorphism?
Show that there exists one. So you don't really need a proof, but you should at least hint as to like why this is true.
Why it's a homo?
Why it's a homomorphism.
It preserves this.
I mean, your easy way out is induction. You're dealing with something infinite. The induction is not complicated.
So I conduct over the number of B's.
Over the.
The length.
I would induct over. Like. Let's see. What's the easiest way to do this? There's got to be some really trivial way to do this. Because you could induct over the total length of AB. Right.
Mm-hmm.
So that's one way to do it. Yeah, that probably is fine. Because, like, think about it like this. What's your base case? They're both empty. So A and B are both empty, in which case H of empty set equals H. So
H epsilon.
Yeah. So try and do the induction from there. Let's see what happens.
So it would be like basis.
Mm-hmm.
And then I have. Let's say I have a string.
Mm-hmm.
So.
One thing I always find helpful to write out explicitly, if not for your grader, then for yourself, is what are you inducting over, right? Because you could induct over the length of, the max length of A and B, like the limit to both, but then the max length of the concatenation of them is 2 times that, right? Or you could or you could be inducting over the total length of A concatenated with B, right? In which case they could be variable length as long as their concatenation is equal to the bound. Right? See what I'm saying?
Yeah.
So you want to be careful when you're doing induction to be clear about what like variable you are doing induction on. In this case, probably like total length of A concatenated with B is a good place to go.
Right.
And if their total length is 0, then both of them must be epsilon, right?
Yeah.
Okay, so that's how you can start your basis case.
Okay.
That's like what allows you to say that there's going to be epsilons everywhere, right?
So should I phrase this as like an XY and
Well, AB. You could just call them AB, right? Still.
well.
Oh yeah,
those
yeah.
are
I
my
see.
letters.
Yeah,
I
yeah.
don't
XY
wanna-
is. I like XY.
don't
It's a good point.
So okay. So it's really
It actually is epsilon epsilon, but
epsilon. Right. That's what I was about to
yeah,
change.
yeah.
It's really this, which is
Equal to the empty set, which is equal to
well.
is equal to h of epsilon, which is equal to empty set. Yeah.
No,
and then
it's
the other
not the
side-
empty set. It's the empty string, right?
Empty string. Yeah, yeah, yeah. Right. Good point. Those are different.
Oh, and you have to do both.
And yep. And the other side is
Okay, so I have h of epsilon,
h of xy, and then
h of xy.
Yeah.
Yeah. It's h.
We're
of
being
x
like stupidly
concatenated
formal
with
right
h of
now,
y
but-
is
Do you mind writing bigger in the future? By the way,
sure.
it's just for.
Yeah, I know. I saw it in the video.
It's fine. They can hear me. So I mean, if they listen to the whole thing, they should be able to get it. But
this is going to be epsilon.
I finally moved the speaker, so hopefully it sounded better. Yep. Yeah.
And now by that it's
Yep.
equal to this. I don't.
Yeah. So okay. So your base case works, but also you can get rid of that w equals epsilon thing. It would have to be x and y both equal epsilon. See in the top line, you still have a w.
Right. X equals
And y equals epsilon.
epsilon.
Mhm.
So
Cool.
induction. Okay. So my
Is assume when what?
my inductive hypothesis is assume h of
Assume if. So it's an if then statement. So it's if what? Or assume that for something.
well, it was going to be assume and then, which is assume
Right.
if. And
So what are
then.
we assuming though?
But we're assuming that I have a smaller string. So xy, I have a string. Let's say with one character smaller. So I could say I have.
You could say n even. Like the x length of x and y equals n is a decent place to go. Yes. So assume. Well, it's assume that if xy equals, it's still an if statement in this case, right? Because it's assume if this, then these two
If.
things, then this equivalence holds, right?
Then I want to add a character and then show that it's
So wait, then what? What is the equivalence we're trying to prove? What are we trying to prove right now? Just overall.
Okay, so h of xy equals h of
Perfect.
x.
Yeah, yeah, yeah.
H of y.
Yep.
And now I want to add a character
Mm-hmm.
and to get a string of length n plus 1
Yes.
and still get this. So I want to say.
Kind of happy you didn't write proof because people would have messed this. This would be a.
I need a new
This is
letter.
not the most trivial induction.
Let's say CXY.
Not a hard one, but not a
So
trivial one.
C is going to be in sigma. And I want to show h of CXY. Let's say want to show.
Maybe it's not a bad thing that it's written small. Okay, so induction. Assume if xy equals n, then this, so
I should say.
not quite. Okay, so here's a pitfall here. The C isn't necessarily the first thing.
Okay.
But what you could argue is that any string of length 1 greater than n can be written as any string, like, so any string of length n plus 1 can be written as a string of length n
And
and something new at the beginning. So you can do this, but only because you can argue that. Because notice that, like.
you can hit the
Yelling at me?
No, it was mine.
Oh, okay. So. notice that, like, what if I have, suppose x and y are like 0, 1, and 1, 0.
Mhm.
If I want to talk about 0, 1, 1, 1, 0, it looks like the c has to go in one of it, like right here,
Right.
right?
Mhm.
But because like you don't actually care exactly what x and y are, you can say, well, this is your new y, this is your new x, and because this is true for all xy of length n,
Yeah.
we know it's true for this.
Right.
So now we just consider, well, you could just put it out.
That's why I think
Does that make
maybe
sense?
you would want to say, okay, now I have x prime and y prime, and then a c
Yeah,
somewhere.
it's not a bad idea at all.
Yeah.
Because it makes it more clear that they're no longer the same object, necessarily. This is a good exercise, though. Like, I'm not saying you have to go through this and this amount of formality in the thing.
Yeah.
You should definitely at least allude to this stuff, because, like, as you're seeing, it's not totally trivial to just be like, and of course this thing holds, right?
Yeah. Which is funny because I'm just trying to show it's a nice homomorphism, and I haven't even gotten to the.
I know, yeah.
to the languages yet.
Yep.
Okay.
Because I think the main point of my understanding is the main point of the exercise is to show a homomorphism for which this works, not to prove that what you gave is a homomorphism, though that's technically part of it. So, like, I don't think we're going to be looking for formal inductions that what you give is a homomorphism. But alluding to some of this is probably a good idea for grade safety.
Yeah.
If it said prove, then this would be a different story and this induction would be necessary. But yeah, this looks like a trivial step, right? Like, when you just like
Yeah.
look at it intuitively. But cool.
It's
Okay.
helping my,
What?
yeah, it's helping my at least understanding now.
Yeah, no, it should A, help your understanding of why it's true, but B, just like in general, you are going to be asked to prove things in this class on tests, on and homeworks, and so like proving everything, at least in office hours, is not a terrible idea. Just for your own understanding of the material.
Yeah, assisted proofs.
Yeah, assisted proofs. So these are primes now, right?
Yeah.
So we do some argument to say, okay, well, notice that like any string of length n plus 1 can be written as a new character from the language concatenated with
Where
a
the
string of
lengths-
length n.
Right. X
And we know-
prime y prime is length then.
Yeah. Okay, cool. So, what's the last step of the proof then? The homomorphism tells us that.
So the
So strong induction is probably what we really want
right,
to do.
it is strong
Oh.
induction because your inductive
No.
hypothesis has to cover.
Here's a nice way to do it. It can actually, you can do it without strong induction this way. You require that, like, length of x prime equals n minus 1.
And then
And
the
length of
right, because now you're abusing
length
this
of
X prime thing.
y equal, I mean, actually you can
Equals
just say
one.
it's n,
and
and then this
is
is empty.
Yeah, that's a huge abuse of the.
But it's fine because this is any string of length n, right?
Right.
And so
Yeah. Y prime.
it doesn't
But,
doesn't
yeah.
matter because we proved our assumption is for any string
Right.
concatenated strings of this length, and so
Yeah, you could, but
so one of the possible pairs of this length is any string
I
x
never
with
feel
empty set.
guilty about using strong induction because isn't it supposed to be logically equivalent to
Yeah,
regular?
it's logically equivalent.
Okay.
Yeah, it's logically equivalent.
But this is a
The
nice.
structure of strong induction is a little more confusing, though, in some sense.
Yeah.
I would say. There are problems like this one where it's easier to use strong induction because you know it's true about like everything in the past. There's something that can be a little confusing about strong induction. One thing that confuses most people is why you can leave out the base case. You don't need a base case in strong induction.
I don't think I even knew that.
Yeah, most people don't. A lot of people will write strong induction with a base case. We can go over that after this problem if you're interested.
Okay.
I went over that in discrete math last quarter because like everybody was just like nobody understood this. But yeah, you actually don't need a base case in strong induction, which is kind of another benefit, but it's a hint as to actually the structure is a little more complex in some sense. Okay,
So
so now we know that. Oh no, sorry, we do want this to be n minus 1, and we want this to be 1, right?
But
'Cause
now
then this
you
is the
want to
strength
move.
of
Now we
like
want to
that.
move x. I think you want to have x prime and y prime together, and you want to have c on its own.
No. This is
No?
fine. This is fine. We so our new. Oh no! Wait, we can't actually have 3 strings. It's just an x prime.
Yeah,
and
x
y
prime y prime is a string on its own.
Yeah,
That's
yeah.
what I meant.
Sorry, yeah, you're right. So really, but you do it like this. You still do it the same way. Right. Okay. Sorry, we got to maintain the structure of things. But you still do it like this.
Okay.
And then you say, okay, well, then.
Oh yeah, this is nice.
And so now you can say what? You can say that by our assumption, this equals, and maybe we do want strong induction. You're probably right. This is way easier with strong induction, but certainly we have that for some like, I don't know, what do we even want to use? X double prime or X double prime? For some x double prime and y double prime, we have this, right? Because this is a homomorphism. Is this how we want to go about it?
I don't know if this gets you to the n plus 1 case.
I don't think it does it?
Because you're trying to show this.
Yeah. Yeah, I don't like that. The best way.
Yeah, I would not be able to prove this.
What's the? I wonder. I mean, I could also be missing a easy non-inductive way to do this, but I don't see it off the top of my head.
So like the only way to do you want
Oh wait,
them to
whoa,
turn out to be
whoa!
epsilon?
We need to use the specific language because we're trying to prove that this is a homomorphism, right?
Okay. Yeah, right. So you
Oh,
want to
okay.
use this
Yeah, we
the
gotta keep our-
definition of H over there.
Yeah. And so let's see if I did break it up the way I wanted to break it up, then things I think will end nicely because of the traits of the function. So this can be split into 2 things. This is either going to be alpha, or it's going to be the empty string. Right? This has the same last character. This homomorphism changes each bit individually, right? So the last bit is either going to be alpha or empty string, and you can kind of just take it out and take it outside the thing, right? In fact, actually, you can just do that. Yeah.
Yeah.
Yep.
Okay, but this
You see kind of how you would do it though. It's like because the homomorphism you've defined acts on each bit independent of the others. Well, the last bit is either going to end you with like this string minus the last bit with an alpha out here, or
Right.
with nothing out here. And the same thing's going to happen over here, and you do the
so
algebraic
you get two
steps.
things of length n that you're saying are
Yeah.
the same, and then you have h of you have like an alpha on the outside
Yeah.
that you're saying is the same, or an epsilon that you're saying.
Yeah.
is the same.
And either way, you either got there's an alpha at the end of both, or an epsilon at the end of both, and then the rest is just of length n. And so by assumption, the rest is a homomorphism, right?
Yeah.
That's like an inductive way to do it, which looks like a pain. The high level way to say it is just like, what's the high level way to say it? It acts on each bit independently already. Like if you put a string in here, what you're really doing is a function on each bit.
Yeah, I really feel like you could show any function that works in this way. That's
Not all homomorphisms are going to.
is any function from sigma to gamma that's surjective. Actually,
I guess it really is that it's working on each bit
honestly, I
independently.
think anything that's a function, as long as you're not mapping a to
Not-
alpha and beta, then
not any function. Not every function is a homomorphism. But this, okay, what did this whole proof even highlight? It highlights this fact is really just saying, like, your function essentially acts independently on each bit of the string.
Right.
Right?
Yeah, you can break them down
Yeah,
until
yeah.
you can't anymore, which is strings of length 1,
Yes.
and then you concatenate them all
Right.
together.
So that is like the high level way to talk about it. This is the proof of it, like why your function. But the reason there is a proof that shows that your function is a homomorphism is because your function acts on each bit independently.
Right.
And that's basically the definition of a homomorphism.
Yeah,
this,
I'm not
this
mapping
rule.
strings to other strings because then you might not
Yes.
get one.
Yeah.
So, okay.
So hopefully
Let's
this
talk-
was at least slightly enlightening. You definitely don't have to do all this. You can just say it acts on each bit independently, and that's sufficient.
Let's talk about languages.
Cool.
Since that's the actual
Yeah.
problem.
Sorry.
No, but this,
Segue.
I feel like you need a foundation on this to really.
You can kind of wade through sometimes and get answers with partial information, but I think it's harder. Like, I've seen people pass things like discrete math without where I see their homeworks and I'm like, it's sufficient for the answering the question, but the way you did this tells me you don't understand certain base level concepts.
Mm-hmm.
And that lack of understanding can sometimes show up in tests where they flub a question that actually needs you to understand that. But so sometimes I definitely see people struggle through even if they're missing certain foundations, but this is definitely helpful when the foundations become necessary. Mind if I erase all this?
Yes,
This
erase
mess?
everything.
You're like, please get it on the site.
I don't know what I wrote.
Yeah. Cool. That was kind of interesting.
Okay, so now we need languages. So I think, or we just need one. You just need A, right? So to keep things simple, you could just define a very small language over sigma star. So A subset sigma star is, I was just gonna put A and A, B in here. And so if we do the homomorphism, H of A, now we can just take each of these.
You should put the equals on the other side, right? Because notice you're saying that's equal to your
Yeah.
your alphabet,
Yeah, I don't.
or the sigma star of your alphabet actually, which is a little dangerous. Yeah, good.
Okay.
Yep.
So if I do H of A, then I'm just gonna process each of these
Mhm.
using the homomorphism. I guess technically you would say H of W for each W in A,
Yeah.
but I'll just write. So A is going to become alpha.
Yep.
And AB is going to become alpha.
Yep.
Epsilon,
Which is alpha.
which is alpha. So I can.
Yes.
get rid of
Yep. It's important to say that step when you're writing a homework, of course, but like to say these are the two you get, but they're the same, so this is your set. Right, and so then the inverse of that is clearly what?
So okay, so I'm gonna say let's call this B the language.
Okay, sure.
And so now when I take the inverse homomorphism of this, so the whole trick to this problem is the way the inverse homomorphism is defined. Which
Right.
we said that this is going to be x in sigma star, the
Mhm.
original alphabet, such that h of x is in B in this.
Mm-hmm.
And so this is the problem. We started with this language
Yeah.
which had 2 strings in it.
Yep.
And now we're getting every string in sigma star, which would end up in B after applying this
Yep.
homomorphism. And so now it's not just A and AB, but this is going to be A, AB, BA, ABB,
Oh wait.
right? Is that not
I
what
don't
happens
think-
there?
One second.
Because all of these, when you
Let me double check. I forgot. Wait. I want to just double check the inverse definition before I make any statements that may or may not be true. X in sigma star such that HX
is in
is in A Oh yeah.
Yeah.
Yep.
So
No. I agree.
okay. So you get every string, just with this specific homomorphism, you get every string that has one A and any number of B's
Yes.
because you've mapped B to epsilon.
Exactly.
So you're throwing out all the B's. So even though you had this singleton language which just contained alpha, its inverse homomorphism is this like infinite
Yes.
language.
Yep.
But the language that you started with only had two things.
Yes. Yeah. You don't even need to describe the full language to know it's different, right?
Yeah.
Like you can, as soon as you show
can
like
get to 3.
ABB is in, well, you could literally just say like ABB's in it. Notice this. And
Oh
like,
yeah, one
right?
case.
It's
Right.
like-
One case could like that wasn't in your original
Yes.
one could violate.
As much as I like to teach how to do things as thoroughly as possible, I also like to point out the ways that you can be a minimalist in some sense. 'Cause
Yeah.
It just helps you like look
But-
for wordings and problems.
So this language that we got
Yeah.
by what we showed in class, like this is regular, because in like we said regular languages.
Yeah. But it doesn't matter that it's regular, right?
Actually, but yeah, no, you don't know that it's regular because
Because
we don't know that.
This problem doesn't tell you
But
to
they're not
make
the
a
same,
language
right?
that isn't regular.
It says make one that's not the same as what you started with.
Right. That's my interpretation
Yeah,
of the problem, and I
exactly.
think that's the only way to interpret it. Whether or not there is one could have been a more complicated, would have been a harder question.
Okay.
Yeah, because either you would have to find a counterexample or you'd have to show closure. Like, you'd either have to find a more specific one, which is the one that breaks down under inverse homomorphism.
Mhm.
But here is an interesting question that makes it easier though. This harder version of the question. If it is the case that you can come up with an A and an H such that inverse H of H of A, right? This thing from the problem
Yeah, that they were
isn't
equal.
regular.
Oh, that they weren't.
That it isn't regular. What does that tell you about H?
What does it tell you about H? So regular languages are closed under inverse homomorphisms. Then
Right.
H of A was not regular.
Yes. But
Is
A
that
is regular, right?
But A is regular, so H, I don't know, it breaks regularity.
Yes. It would be the proof can be simplified to just talking about H because we already know that H is closed under inverse homomorphism.
Mm-hmm. That the regular languages are
So
closed
yeah,
under
it would be
inverse.
essentially equivalent to saying that that H is not regular. And that the transformation that H does from here to here is not a regular.
Right.
It doesn't create a regular language.
Okay.
So
And-
that would be the simpler version of it.
So yeah, like this is injective. Do you have a problem if your gamma is like huge and it's not surjective?
We're talking about the harder version of the problem of if there's an H such that
Well,
is there a homomorphism H and a regular language A such that H of A is not regular, right? That's the question right now.
well, does H's ability to preserve regularity have anything to do with whether it's injective or surjective or bijective?
Injective. So, surjection shouldn't matter. Right, injective shouldn't really matter. Injective is everything gets mapped to at least once.
No, that's surjective.
Okay.
So yeah,
Anyway,
I think
surjective shouldn't
injective. I
matter.
think they have to be injective because if it's not injective, that means you're mapping something in the original language, in the original alphabet, to two things in the or more. Injective is 1-to-1.
So there's no function that maps
So it's not-
something
not a
to two
function.
things. It's not a function.
It's not a
right.
function.
Yeah, that wouldn't be a function. It doesn't matter if any symbols are not mapped to in gamma,
Okay.
because then they would never appear
In the language.
in H of A.
Right.
Right? We're not
the
not-
image of the homo. Yeah, he was using image and pre-image.
Sure.
I don't know these things.
Then in the image of the homomorphism, they wouldn't appear, so they don't matter,
Okay.
right? The only weird thing that can happen is what you did, where you map something to two things.
I map two things to one.
Sorry, two things to one thing, like more than one character
Right.
to a single character,
Mm-hmm.
which shouldn't be an issue, honestly, for regularity.
Yeah, it didn't, like, all of the languages we looked at were regular. They just weren't the same language.
I can't think of the proof off the top of my head, but I presume that they are regular. I would be surprised if H of A, if there exists a regular language A and an H, a homomorphism H, such that H of A is not regular. Because I think you can prove it reasonably.
Well, but he's saying, so Theorem 7 doesn't say that if H is a homomorphism and H of A is regular, then A must, then A must be regular.
Wait.
So he's saying he didn't do this,
Okay,
maybe because
okay.
it's not
Give me a
true.
sec. Well, he's actually saying even if you know H of A is regular.
Then A.
It's saying that A must be regular. Oh, that's
Yeah.
a totally different question. Okay, yeah, because H of A, if A is regular, H of A is definitely regular.
Okay.
But A doesn't have to be regular
For H of A to be regular.
for H of A to
Okay,
be
that's,
regular.
okay.
Which makes way more sense. I was like, I cannot think of any kind of crazy, like, it seems pretty
Because
easy to prove.
your
that-
homomorphism could fix irregularity by eliminating whatever, like, complexity that was causing it
Yes.
to not be regular.
Yeah, that's right.
Okay.
So, that's probably what he's gunning for and looking for.
Yeah, I'm thinking he's gonna show that, you know.
I think that's what he maybe wanted, but he definitely didn't ask that on exercise 7.5, right?
Well, we don't know any non-regular, like we haven't moved
Oh,
up.
that's true.
We haven't moved up yet.
Yeah. So you would have to, like, go ahead in lectures to even do this the harder way.
Yeah.
But yeah, so probably something better thought about once you learn about not regular languages, but is an interesting exercise to consider once you learn languages that aren't regular. Because you'll learn about the properties of languages that tends to make them not regular, and so it'll make this problem easier. Or the harder version, I should say, this problem easier.
Oh, yeah, right underneath he shows that regular languages are closed under homomorphism.
Yeah,
A is
'cause
regular. Yeah.
I mean, that makes way too much sense.
That's me forgetting,
I also, I clearly did not read past the exercise.
me forgetting the rest of the lecture.
That's funny. Yeah, this is exactly what I imagined. this
Yeah,
type of
having
thing.
not taken algebra, this was the point in the class where I was wondering what the hell was going on.
I see, fair.
So,
But yeah, so, I think I can stop recording anyways,
Okay.
because we've talked way past what people even needed for the problem.